Hi, my name is Anry, and today we're going to be talking about the first law of thermodynamics, what it is, and how to solve equations using it. Now before that, let's have a short refresher. What does the word thermodynamics mean? Well, let's find out. Thermodynamics comes from the Latin words thermo, meaning of heat, and dynamis, meaning power. Literally speaking, the word thermodynamics means the dynamics of heat. Alright, that's all fine and dandy, but what even is thermodynamics? Well, thermodynamics is a branch of science, and the study of the relationship between heat, energy, temperature, and work. Keep in mind that heat is a form of energy, so we call that thermal energy, or heat energy. Therefore, thermodynamics deals with the transfer of said thermal energy from one place to another, or from one form to another. Now there are four general laws that you could say are the linchpins of thermodynamics as a branch of science. These laws describe the different ways that temperature, energy, and entropy can interact with each other, and how the energy in a system changes, as well as whether the system can perform useful work on its surroundings. Of course, for this lesson, we're going to be tackling the first law, so let's dive in. The first law of thermodynamics, otherwise known as the law of conservation of energy, states that, within an isolated system, the total energy of the system is constant, even if energy has been converted from one form to another. Now what does that mean? Now, energy cannot be created nor destroyed. Instead, how energy works is it either is transferred somewhere else or it's converted to another form. So basically, the first law of thermodynamics is saying that, in a system, energy may be transferred in or out of it, and even converted into different forms, but no energy is ever created or destroyed. Another way to demonstrate the first law of thermodynamics is with this equation, delta U is equal to Q minus W. Now this equation can be read like this. The change in internal energy of a system, delta U, is equal to the net heat transferred into and out of the system, Q, minus the net work done on it, W. So let's have an example so we can break this equation down and really understand what that means. Now, as you can see in this example, gas particles are heated and compressed in a cylindrical container equipped with a movable piston. The total kinetic energy of the gas particles is considered the internal energy in the system, denoted as U. Now, for this example, let's assume that the gas in the container is an ideal gas. Now let's say that the internal energy of the system changes. Well, we denote that as delta U, as in the change in internal energy. Now how do we know it changes, and by how much? Well, when one compresses the gas using the piston, it exerts work, denoted as W, on the system, transferring energy out of it. Inversely, when one adds heat, usually the symbol for heat is Q since H is reserved for enthalpy, the system's temperature rises, bringing more energy into it. Therefore, the change in the internal energy of the gas is equal to the heat added to it, minus the work done to it. Now let's see what that looks like in action. So in this problem, 560 joules of heat is added to a system. The system then does 280 joules of work as the gas is compressed. What is the change in the system's internal energy? Well, we have our equation here, delta U is equal to Q minus W. The change in internal energy equals heat added minus work done. So we're solving for delta U, so let's find the heat and work done in the problem. So we have 560 joules of heat and 280 joules of work done. Plugging those numbers into their respective slots in our equation gives us delta U is equal to 560 joules minus 280 joules. And that equals 280 joules, which is how much the energy in the system changed from its original state. So let's run through another equation so you really get the hang of it. Now in this problem, 3000 joules of work is done on a system as the gas in it is compressed. Afterwards, 2300 joules of heat is removed from the system. What is the total change in internal energy? So we have our equation here again, but there's a catch that makes this problem different from the last one we just did. Now notice how the problem says that the heat is being removed from the system rather than being added to it. We denote this by writing the value of the heat as a negative value, because remember, heat is a form of energy. So a negative value means that we're taking energy away from the system. We're removing it from the system. So, we write our equation down as delta U equals negative 2,300 joules minus 3,000 joules, which when solved gives us negative 5,300 joules. Now, for convenience sake, here's a table that shows when the values of each variable in the equation for the law of energy conservation should be written as positive, negative, or 0. And now for the part you've all been waiting for, the activity. Now I want you to answer these questions and see how much you've learned during our discussion. But be warned, these questions require a bit of extra thinking. Remember to refer to the table I gave you just now so you can answer them. And that just about ends our discussion on the first law of thermodynamics, otherwise known as the law of energy conservation. Now I hope you've learned something from this, and I'll see you soon.